All right, team, here's what's going on. I have a few topics here that are fundamental topics to not only MAE 201, but also your future class MAE 213, Physics and Calc 3. If you do not understand these topics, those classes will be drastically harder. You cannot just get away with knowing how to calculate these and solve the problems for the exam, but you need to understand the physical aspects behind what these mean. So let's get started. A coordinate plane, you're used to this. You're gonna see an X and a Y in 2D space. Obviously, you can have some random function. As X is doing something, Y is doing something. So as X increases, Y is increasing, then decreasing, then increasing. Now, in this class, you see a completely different version of this, and in Calc 3, in which you will see a Y, an X, and a Z. And I have brought up a model for you. The X and Y is no longer this back plate. Many students struggle to understand that. This X is no longer an X right here. So now instead of just having the X and Y be this back wall, we now have X and Y being the bottom floor. So when you see this coordinate plane in calculus, physics 1, physics 2, in this class, you need to understand that the XY is now the floor. Pretend that this is a room. The X and Y is the floor. The XZ plane is the left wall, and the YZ plane is going to be this back wall. So if you have a vector inside this room, you know you're gonna be all positive numbers. If it is behind this wall, this imaginary wall, that's gonna be negative in the Y direction. If it's behind the back wall, it's gonna be negative in this Z direction. And if it's underneath the floor of this room, you're gonna have a negative Z direction. So it's fundamental to understand that in 2D space, the X and Y, while Y may mean up, in 3D space, Z means up and Y means to the right. So hopefully you got that. Let's continue. Now, by now you've been working on a lot of equilibrium setups. What is equilibrium? It is when we have a point and we have many forces coming around to it. And because of the law of physics, we have decided that this is not going to move. Because this does not move, we are saying that all of these forces must equal each other, because force equals mass times acceleration. If acceleration is 0, that means the sum of the forces must equal 0. So let's start thinking about how we can lay this out. This is going to be a guideline for your quizzes, your exams, and your homework. That will not only make it easier for you to keep track of your work, but it will make it easier for you to double check it, and it will make it easier for the graders to look at it. So first things first, you want to create this table. Let's imagine we're going to use this right here. And we're going to label this force 1, force 2, and force 3. We are only in a 2D space for now, X and Y. So we're going to put X and Y. Keep in mind these are the I hat direction and the J hat direction. Then you will take however many forces you have, in case we have 3, and you're going to label them in this column right here, F1, F2, and F3. X in this case is positive, Y up is positive. If we go to the left, we're X negative, and if we go down, we're going to be Y negative. I'm just going to use variables right now, but in your homework you're going to have numbers. So in this table you'll probably plug in numbers, but for now I'm not going to talk about numbers specifically, just the idea of how you should lay out your work. So force 1, what we have is we're going to have a number here in the X. And what value is this number going to be? This is going to be a positive number. Next, we're going to have Y. It's not going in the direction. So in this case scenario, we will not have any direction, so it's going to be 0. But in another case, like F2, we have some projection in the X direction. So we're going to have a positive number here, and then we're also going to have a level of force coming up. So we're also going to have a positive number here. Again, these will be numbers in your cases most likely. Sometimes you'll have to use variables to solve for these problems, but imagine you plug in some value into here. Last thing, we have F3 right here, which is going to be in the negative X direction. So we know for a fact we're going to have a negative number here, and we know for a fact we're going to have a positive number here. Great. What this allows us to do is not only keep it in a nice organized table right here, but it allows us to check our signs. Before you even think about doing any calculations, I want you to take this step. I want you to look at this vector and go, great, we should only have one number because we're only in one direction, and it should be a positive number. Do I have a positive number in here? Yes. Great. Next one. This should be two positive numbers, right? Because we're going up and to the right. Great. We should have two positive numbers. This allows me to check if I've made a sign mistake, because many students make sign errors before they start the calculations, and you've already screwed yourself before that. So on this one, we're negative, so I know for a fact in the X column, I should have a negative number somewhere. If I see a positive number here, and I'm looking at this, I know I've messed up. And this allows you to check your signs before you even run any calculations. Again, let's carry this out to 3D space. If we have a thing here, it's pulling, we'll say this is, it's gonna be hard to know, but this is going to the right, it's going to come outwards, and it's going to go up. Sorry, I'll just draw like this. So right, up, and then up. So this is inside the room. So we'll also have a Z direction, and we'll say this is like a completely different problem. So we'll pretend we don't have these here. This is a new problem, but we're gonna name this F4 just so you don't mix it up with this. We should now know we should have three numbers here, positive, 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 right here. Great, I can easily just look at my vector from my diagram and know that it's a positive number. Moreover, if I have something that's completely down, this is now going underneath the floor. You'll have nothing in the X, nothing in the Y, because we're not going anywhere here. And we know we should have a, this is F4, we'll do F5 here. We know we should not have a number here, and we should not have a number here, and we should have a negative value right here. So if you don't have a negative number and you're looking at this, you've instantly identified that you made a mistake. Now the last reason this is a really good graph to use, or table to use, is because now we can do some of the forces in the X, some of the forces in the Y, and some of the forces in the Z. How do we convert this? All we do is we're gonna take this number, F1, times whatever value we have here, and you're gonna put it here, F1 times whatever number we have, plus F2 times whatever number we have. And again, we have a positive number, so F2 times a positive number here. And then we're gonna go et cetera, et cetera, et cetera. So now you have F1, F2, F3, F4, F5, et cetera. And you are going to convert this entire column into this right here. Now what we have done is we have created a matrix just like this, where you're gonna have all these set equal to 0, so your matrix is gonna go 0, 0, 0, right? Because some of the forces in the X, Y, and Z direction are 0 for an equilibrium setup. Your columns now look like this, F1, F2, F3. Now that you have your table, you're gonna have your F1, F2, and F3, great? Then when you do reduce row echelon form, you're gonna get three values, F1, F2, and F3, and you've finished your problem. So this is much neater using this table, making sure you have your signs correct, converting it into sum of forces X, Y, Z by essentially just moving it down right here. And then you can just plug it into your calculator and you're done. Okay, now we're gonna talk about unit vectors, but before we describe what the unit vector is, we have to remember that a vector, a standard vector in I hat, J hat, and K hat is going to be a magnitude and a direction, plus a direction. So what we are doing when we have a unit vector is we are going to then take this term right here and we are going to divide it by the square root of the I hat squared plus the J hat squared plus the K hat squared, right? This is now converting a vector into a unit vector. And again, a unit vector is U hat. So now let's think about the theory behind a unit vector. In 2D space, we remember the unit circle. At any given point, this radius is going to be 1. So you can use trigonometry, cosine, sine, tangent to then explain in the x and the y exactly where are we pointing. So it's just a direction, right? Cosine, trig, and tangent, if you take the magnitude of them, you're gonna get 1. That is because then, when you multiply it by a force, you are not changing the actual quantity of the number. You're only describing the direction. So a unit vector, again, is we get rid of the magnitude and you're gonna have the direction. Likewise, in 3D space, y, x, and z, you can imagine you have a sphere. And in this sphere, you have your vectors coming out in 3 dimensions. And all of these are going to be of magnitude 1. So again, it's just like the unit circle, but in 3D space, is what we're doing to this vector is we are turning it into a direction only, so that no matter what magnitude we have, we don't change its direction. So let's write out this formula right here, which you'll see a lot. This is a force vector equals a magnitude of a number of a force times your unit vector right here, u. We'll break these into components. If you see a force vector, you're gonna have an x, y, z component. Then you're going to have a singular number right here of a force. Then you are going to also have another x, y, z right here. The difference between these two is this right here is just this right here. It is a magnitude and a direction. When we do the square root and turn it into a unit vector, then this entire term is going to be this one. So this is going to be your direction, this is your magnitude, and then this is your vectors, both magnitude and direction. So let's put this into a theory right here. This is a rope right here, and I'm going to pull on this rope at a certain force. Now let's add another rope, but this rope is longer than the first rope, and we're gonna pull on it at the same force. So these are gonna be equal. We both know that no matter what we do to this rope in length, if we shorten it or lengthen it, we're still pulling at the same amount of force. But we need to define what direction we're pulling this rope in. Because again, in 3D space, we could be pulling on the rope this way, we could be pulling on the rope this way, we could be pulling on the rope this way. If I just give you a number, you have no idea where I'm pulling. So that's why we need the direction term. This will now give us a magnitude and a direction. However, if we do not do this right here, and we increase the numbers in here, what's gonna happen? It's going to increase right here. Again, let me repeat. If you have a number here, and you do not vectorize it, and you multiply it out, and you increase the numbers here, which is increasing the length of this, that is going to increase your force vector, which we know we can't do. If we increase the length of this rope, we shouldn't be increasing the amount of force that we're pulling. Now, it is, if you take this magnitude right here and you divide it to this, to get this, we are now saying that this, the magnitude of this, is going to be equal to 1. So now, no matter how long we make our rope, this number is not going to change this value. This is now defining a direction without changing the actual output of force. What we're saying again, I'm going to repeat that. You have a force and you have a direction. When you divide and you take the unit vector of the original vector, you are making this 1, and you are then defining a direction of your force without changing the actual output value. The next thing people struggle with is calculating torque. Now, likewise, what is a torque? It's essentially a rotational force that is applied on an object. You guys learned to calculate that using the formula R cross F. What does that mean? It means at some radius, we are going to apply a force right here. So now this becomes R, and this is your F. Then we're gonna name this point A right here. So now let's think about the physics behind this. You're applying a perpendicular force at some distance from R. Now, let's think about a bolt on a car. If I take a force and I push this way, and I'm trying to turn a bolt, and I push the wrench in this way, nothing's gonna happen. You're not gonna actually change the bolt in any way, shape, or form. So that is why we only care about the perpendicular force. So now let's think about it again. We have our wrench, we have our bolt, and say we have a force right here. We know for a fact that this force is going to move into two components. It's gonna have an X component, and it's gonna have a Y component. We only ever care about this Y component. We only ever care about the perpendicular force acting on it, because the X component is not going to actually have any effect on the bolt. So whenever you see a problem, which you should have recently seen a problem that looks like this, you're gonna have a few forces on it. You're gonna have a force going this way, and you're gonna have a force going down this way, and then you'll have a force, say, going this way right here. All of these are gonna have an X and a Y component. So this perpendicular force is us pushing down on the wrench, which will affect the bolt. It will tighten the bolt. If we push down this way, it's still pushing down in this component, but we're also pulling this way. Again, let's think about it. If we pull on the wrench, the bolt's not gonna move in any way, shape, or form. If we push down on the wrench, it's actually going to move the bolt. So we don't care about any force that is in line with this bolt. So anytime we're pushing a force into the bolt directly, like this, it's not going to have any effect whatsoever. It has to be at some distance, r, at a force that is completely perpendicular to the radius. Now, this goes along with the right-hand rule. Now, what is the right-hand rule saying? It's saying, what value is our torque or moment going to be? Is it going to be positive or negative? The way I think about this is you're going to have your radius right here, and then you're also going to have your force. And this is your force. What we will do is we will follow the radius. So let's start at the point that we're taking the moment about. So usually A, or the origin. You'll take your hand, you'll place it at the origin, you will follow the radius to the force, and then you will curl your fingers in the direction of the force. Once I have taken my hand and followed the line, pull up, what direction is my thumb facing? It's facing up, and that is a positive value. Forward, up. So then, in the other case right here, my fingers come this way, but they don't curl back. So I have to then put my hand like this, follow the radius, come down to the force, and curl. Which directions are my hand curling? Clockwise. So let's summarize this force. This force is applying an X component and a Y component. So we don't care about the X because it's in line right here. If we pull on the wrench, it's not going to do anything. So we only care about this force coming down. So we follow our fingers, go to the force, so we rotate. Where is my thumb going? It is going into the board. So now I know that the torque about this point as a result of this force is negative. The last thing students get tripped up on is understanding exactly how to follow this. It's just like vector addition. If R is a vector and force is a vector, and you add them together, you're supposed to do tip to tail, right? If you add this vector plus this vector, you're supposed to add the tail end of the one you're adding to this. So again, that works right here. You're going at your origin, you're moving this way, you added the force, you watched your fingers, and that was good. They then get confused if the force vector is this one right here, and this is your radius. They want to then follow the radius and go up to the force, but we cannot do that because you're going up to the head right here. So what you can do is you can imagine that there is an infinite line right here. No matter where, if I pull on this distance, radius, if I pull on the bar right here, or if I push on the bar, the effect is going to be the exact same. So you can visualize sliding this vector downwards onto here like this. They're the same vectors, and now we can then go radius cross F, radius cross F. My fingers are curling down towards F, my thumb's down, so it's negative. Never ever follow the radius out and then go from the head to the tail of the force. So I hope this helped I hope that you understood these topics. If you do not understand these topics, please email me, skyork1@asu.edu. I can reach out. I have office hours from 4:30 to 5:30 on Wednesdays. So reach out to me if you have any questions. If you don't understand these topics really well, it's gonna come back to bite you in the butt. Thank you for watching. Have a good rest of your day.